Our last speaker in this morning session is Alex Bradbury, the compiler engineer at Igalia. He initiated the upstream RISC-V LLVM effort back in 12-16, and last year at the RISC-V Summit Europe, he received the Software Contributor Award.
No, I'm good. I'll go here. Okay, thanks very much for the introduction. Obviously we've got RISC-V, vectors, code generation, and LLVM. I know it's a very varied audience here, and 15 minutes to cover it all. I was a little bit, maybe a bit anxious about how to, cover it all in this talk. I think what's nice about a lot of these compiler optimizations is that even if there's a lot of blood, sweat, and tears that goes into actually wrestling the compiler into doing what you want it to, there's a lot of intuition in terms of knowing what the compiler is generating now versus where you want it to be. So I'm leaning on that quite heavily in this talk. So I know I'm what stands between you and the coffee break, so I better dive into some of the things that we've been looking at. Now, this is oversimplified, of course, but broadly speaking, the path of development for code gen for RISC-V Vector, you start with some degree of initial experimental support, getting it to the point that the compiler can generate code for the vector ISA. It develops to the point that you can enable it by default, so you don't have to go and find obscure flags to start using it. We had some additional refinements to the vector specification, additional extensions, and more of the work over the last 18 to 24 months or so has been around further tuning or improvement of the performance. This is clearly, as you know, with performance tuning in compilers, it's not going to be a surprise to say that this is a large task, and to some degree it's never going to be done. There's always going to be more optimizations, new workloads, new microarchitectures, but it goes through stages. We've perhaps been working more on the obvious things, where it's clear that for any microarchitecture we could do a better job of generating the RISC-V vector code. Now, your compiler is taking some input, it's producing output, and it's doing so with an objective. Sometimes it's around code size. Very commonly you want it to produce fast code if you can, please. But it's not something that the compiler can do in a general purpose compiler at least, can do at all costs. It's not like you can have if you have a particular loop nest, a general purpose compiler isn't going to take 10 hours to analyze it and try and figure out the best way of doing it. So we rely heavily on heuristics to try and make the best choice that we can at each stage in the compilation pipeline, in the hope of producing code that's reasonably good and often very good. So there's a few things that the compiler is trying to do during its code generation journey, or different things that we're trying to keep in mind. We talk a lot about profitability, as particularly looking at vectorization. And in compiler speak, this is really when you're looking at a transformation that you want to do, is the code that you, or at least or the intermediate representation, typically at that point, is the transformation you're doing, does it produce something that's better than what you had before? It sounds like a very obvious thing, it's a very clear aim, but it can be surprisingly difficult to figure this out as you go through the compilation pipeline. And I think particularly for scalar and vector code, often you start with scalar input. You're looking to see if you can auto-vectorize it, start to introduce vector instructions, but you have to worry about things like the overhead of switching between scalar and vector registers, particularly if you can vectorize only some of it, but you can't vectorize other pieces. And as I say, you're using heuristics. You're looking at trying to make the best choice you can at this moment, and you kind of have to look into the future a little bit and see, well, I'm going to do this transformation, but often you're going to be running additional optimizations after the fact, and you want to try and make a best guess about what the code will look like after you've done those. There are some other things a little bit more specific to the RISC-V vector ISA in general. So the RISC-V vector ISA, we have a 32-bit instruction encoding, but you could look at it as being logically like the instructions are a bit wider, but some of the control for those instructions is stored in a control status register. If you're a bit too naive about how you handle that in the compiler, you risk doing additional CSR switching, and that's adding unnecessary overhead. Spilling is when you have items in registers, you end up loading and storing them to the stack. naturally any compiler wants to do as little of that as possible and do as much as possible in registers. There are a few challenges where it's maybe more unique to the vector ISA in terms of minimizing spilling. So at the moment in the standard RISC-V ABI, there aren't any Corley saved registers, so there's risk of you end up having to spill around function calls. You also get some more pressure on the register allocator for GPRs because we don't have things like immediate offsets for vector loads and stores. We can end up, there are cases where the compiler could do better, but maybe doesn't right now. And more generally, the compiler has this task of trying to exploit all the features of the RISC-V Vector ISA to the extent that it's able to. One kind of final point of order before I kind of dive into some of these optimizations, I should highlight that this talk is giving a overview of recent improvements that's covered contributions from all sorts of companies, not just me and my colleagues at Igalia. So it's credit to the whole community who've been driving that forwards. And in terms of looping back to exploiting the capabilities of RVV, I was asked before this talk, is it more about autovectorization? Is it more about kind of explicit vector code generation? And I think really it's often both, and they can be more related than you might first think. If the compiler is looking to try and vectorize a loop, and it's looking at the cost model, so how expensive it might be to execute the loop once you've vectorized it, sometimes it gets a very high cost and it chooses not to. Sometimes that's because the cost model's wrong, or sometimes it is very costly, but it's because the compiler only knows how to generate not particularly good code for that pattern. And so if you go and add the necessary logic so the compiler can generate better code, you've just improved both the autovec pipeline as well as explicit vectorization. Now, the intuition between these next two optimizations is kind of the same. We talked this week about 15 years of RISC-V. We had the cake cutting ceremony. If you cast your minds back to around 2014, 2015, and probably almost any vector ISA presentation you've seen since then, from when it was first presented, I think it's characterized by having slides, example code, where you have very nice, relatively easy to read, and once you get past maybe some slightly foreign mnemonics, loops that can handle irregular inputs, so not just a kind of fixed width. And the headline for both of these really is going from generating loops, generating code that doesn't take full advantage of this, to generating code that looks much more like the little snippets and examples you will have seen on slides throughout the course of the development of the RISC-V Vector ISA. So this is at this point I'm talking about, in LLVM we have what's called the superword-level-parallelism, parallelism. This is if you have fixed width vectors and you're looking to parallelize things within a single loop iteration. If you're looking to brighten every pixel of an image, this maybe isn't like the ideal way of doing it. So it's a kind of noddy code example to give an example to show a case where this kicks in. Previously, because the LLVM isn't, other architectures can't support this non-power of 2 vectorization, it would end up just vectorizing the 2 elements. So you have RGB pixels, so 3 elements, and then handle the third one via scalar code. But now, as the work has been done to go and provide support for the non-power of 2 vectorization, we can handle them all at once in the natural way that you go and handwrite yourself. And it's similar, but maybe a little bit more involved for what we call VL tail folding. We're now talking about LLVM's loop vectorizer. So imagine you have a loop, you're going through some number of input elements. You typically handle that when you vectorize it by strip mining it, or you might look at it as chunking it. So you're trying to grab some number of elements at a time and loading them into a vector, handling them at once, grabbing the next set of elements. And previously, this would be done in a way whereby so if you have a vector which has an irregular length, you then have to worry about how you handle the elements at the end of it, so the ones where it's not a fixed multiple of your chunk size. RISC-V Vector ISA naturally gives you a lot more flexibility in terms of how you do that. In fact, full flexibility in that you can go and easily handle these irregular loops. So previously, you'd had CodeGen. You can see at the top, you're handling the vector elements, and then if you have anything left over, you branch to what we call the scalar tail to handle anything that's left over. Now it handles it all via the vectorized loop. And we wondered a bit in the earlier days, like, does this, for sure it generates nicer looking code. Does it matter that much in practice? For some benchmarks, not at all, because if the scalar tail is never encountered, you never execute it, it's just a code size thing. But particularly things like X264 in spec, there's quite a few cases where you have irregularly sized loops and you were spending a lot of time in that scalar tail and almost no time at all in some cases in the vectorized body. There's a number of other optimizations that are maybe a little bit more obvious. It's common to expand things like memcopy, memset, memcompare inline in cases where you can, particularly where additional knowledge such as the alignment or the size means you can do it with just a few instructions, much cheaper than having to call into the general purpose function that's then got to go and analyze aspects of its argument. Also support for some of the newer RISC-V extensions, particularly things like the BF16 or half precision floating point. There's some trade-offs there in terms of teaching LLVM more about widening them to F32 in order to do optimization, in order to do calculations still in vector registers, but where we don't have native support for those narrow operations, which for BF16 you don't really have support for anything in particular unless you might have some multiply add support. And other improvements as well, if you're interested in diving more into kind of the internals of CodeGen in RISC-V and LLVM, my colleague Luke gave a really good talk at Your LLVM that's up now on YouTube about this VL optimizer pass to try and reduce VL to only what's demanded. There's some fun work that landed on LLVM exegesis, which is a tool to benchmark the microarchitecture, give you numbers, throughput and latency and things. It's a little bit helpful with the SpaceMit X60. It's nice to be able to validate the numbers that you might see in manuals. It'll be a lot more helpful as more and more RISC-V vector compliant hardware becomes available for us to play with and use. And in terms of figures and numbers, this is what the improvement looks like over time. I'm looking at Clang as of a few months ago compared to Clang 18 months before. With spec benchmarks on the Banana Pi, so the SpaceMit X60. So there's about, I think it's 12 out of the 16 benchmarks have improved by 5% or more, about 7 by 10% or more. If you want to look how we compare versus GCC, this was work that kind of happened. It was finished, as developed more recently since I submitted these slides. There's a blog from one of my colleagues on the RISE blog that looks at where we stand versus GCC now, where thanks to work that he and others done, we're ahead of GCC on about 11, 12 of the 16 benchmarks, similar for 2 or 3, and GCC is a bit better than us on the others. None of this work is usable unless it's tested continuously. You want to ensure that the compiler works just as well today as it did yesterday. Particularly when we were developing the support for these new configurations, it's important to have ongoing testing of these things over time. I've got this thank you to RISE for supporting that work. I was able to massively flesh out the infrastructure that we have. There's more to come. You can look at the online dashboard we have. It makes it easy to see all the configurations that are being tested and their current status. It was all green before I came on the stage. Hopefully that's still true. In terms of future work, we probably don't have time to discuss much in detail. I'd say some of it is already happening or has landed, like the scheduling model work that Mikhail did on the SpaceMit X60. You could imagine developing that into or some kind of default generic scheduling model due to aspects of how LLVM is implemented. It pessimizes various parts of CodeGen if you don't have any scheduling model at all. So it's common to pick something, say a reasonable in-order core. Used to use the A55, they use one of the newer ones now, on the basis that it helps quite a lot for the in-order designs and it doesn't hurt the out-of-order ones. And finally, I particularly want to echo the comment made earlier from Larry in terms of celebrating what's been achieved. This list of companies, it's just those who have been more involved into this more recent work. The list of historical contributors to RISC-V LLVM is much larger. We've come a really long way. I see it as a great example of collaboration across companies within the RISC-V community. There are for sure companies who do a lot of stuff with RISC-V but haven't found a way to contribute back to the compiler. I hope that will change. But yeah, I'm also really happy about where we've come since I started this back 2016 or so. So thank you very much. I've got a poster up on the top floor, and I think we're probably encroaching on the break time. So yeah, please do come and chat to me there. Thank you.